So good morning students. Today we will see magnetic materials, few problems, how it can be solved. So a brief about different types of magnetic materials is first dealt with, and then we will solve the problems also. So classification of magnetic materials. Magnetic materials is basically classified into five types. Okay, diamagnetic, paramagnetic, ferromagnetic. Actually speaking, these are the basic three classification. The remaining two are the extensions of ferromagnetic material, that is ferrimagnetic and antiferromagnetic material. So you would have learned up to in schooling itself the basic three materials, that is diamagnetic, paramagnetic and ferromagnetic. So in a diamagnetic material, the electron orbits are more or less random, and mostly all the magnetic moments are cancelled. Similarly, all the spin moments are paired, almost paired. That is, they have even number of electrons and has equal number of electrons spinning in two opposite directions. So what will happen because of it? The net magnetic moment in the diamagnetic material is zero. So that is the major distinction. Okay, net magnetic moment in the diamagnetic material is zero. Therefore, most of these materials do not have magnetism in the absence of magnetic field. So only when you apply magnetic field, you will be able to see the magnetic behavior of the material. Otherwise, we won't be able to see. So that is the significance of diamagnetic material. Now coming to the paramagnetic material. Now when I am talking the next classification, I have to take both together, that is paramagnetic and ferromagnetic. So in these two, there will be net diamagnetic moment in the absence of magnetic field also, which means even if I am not applying any magnetic field to it, it will show the magnetic behavior. That is the speciality of these two materials. Now you can ask, when both are showing, then why two different names as paramagnetic and ferromagnetic? The answer is very simple. One is little weak, the other one is very strong. Paramagnetic is little weak and ferromagnetic is very strong. So in the case of paramagnetic material, this spins in two opposite directions will not be equal. Okay, these spins are not equal. Then there exists some unpaired electrons which gives rise to spin magnetic moment, and hence the resultant magnetic moment will not be equal to zero. However, in the absence of external field, the magnetic moments are oriented randomly. So due to its random orientation, some magnetic moments they get cancelled, and the material possesses very less magnetization in it. But the point is, it possesses magnetization, whereas diamagnetic do not possess magnetization in the absence of external magnetic field. So there comes the difference between dia and para. Okay, now coming to know about some properties of diamagnetic material. They repel the magnetic lines of force. Then if you talk about the susceptibility, susceptibility will be negative and it is independent of temperature. Then if you talk about permeability, permeability is less than 1. There is no permanent dipole moment, and so they are very weak magnets as far as diamagnetic material is concerned. Example is gold, germanium, silicon, etc. Then coming to paramagnetic, if you talk about the properties, the magnetic lines of force pass through the material. Magnetic susceptibility is positive and is also obeying the Curie-Weiss law. What is Curie-Weiss law? Chi is equal to C by T minus theta, where what are all the terms? C is the Curie constant, T is the temperature, chi is equal to C by T minus theta. Okay, so chi is the susceptibility, C is the Curie constant, T is the absolute temperature, theta is the Curie temperature. Then if you come to talk about permeability, it is always greater than 1 and they possesses permanent magnetic dipole moment. Then when the temperature is less than the Curie temperature, this paramagnetic will become diamagnetic material. So the examples to quote copper sulfate, manganese sulfate, platinum, all these are the examples. Then coming to the ferromagnetic material, in ferromagnetic materials the number of unpaired electrons are more. Most of these spin magnetic moments point in one direction. Hence, even in the absence of external magnetic field, the magnetic moments align themselves parallel to each other. See, if I have to show the example in terms of picture, say the spins are like this, okay? Randomly in all direction, it will be like this. The spins are like this. Like this it will be, okay? Now, if I am applying the magnetic field, if it is the case of paramagnetic material, what will happen means all the spins will try to align along the direction of the applied field, but it will not align perfectly. But every spin will try to orient itself towards the applied field direction. Maybe like this, maybe like this, maybe like this. So some part of the spins are aligning themselves, at least they try to align themselves parallel to the applied magnetic field direction. This is for the case of paramagnetic. But whereas for the case of ferromagnetic, in the beginning it is going to be similar to random arrangement. Then when I am applying magnetic field along this direction, all the spins will align perfectly along the applied field direction, which means this is very, very strong. That is what we say. Okay, very strong magnetic field. Then, and also a small magnetic field is enough so that all are aligned parallelly. Okay, that is the speciality. So it is a very strong magnet. Even to say about its properties, some magnetization is always existing in all these kinds of materials even before the external field is applied. That is the major or very significant property. They have permanent dipole moment, so they act as strong magnets. Then they exhibit magnetization even in the absence of external field. This property is called spontaneous magnetization. Then its susceptibility is positive and also very high. It also obeys this Curie-Weiss law, chi is equal to C by T minus theta. When the temperature is greater than the Curie temperature, ferromagnetic material becomes the paramagnetic material. Then permeability is much greater than 1. If you take the examples, it is nickel, cobalt, ferrous, all these are the examples for ferromagnetic material. Then antiferromagnetic material is exactly opposite. That is, the spins are like this. The alignment will be like this. That is equal magnitude but in opposite direction. Ferrimagnetic means not equal, unequal in magnitude but opposite in direction. So we don't have much about ferrimagnetic and ferromagnetic, antiferromagnetic in our syllabus. Just to introduce, I am just telling this. So this is about the classification. We will see further details in the next slide. So let us read the problem. A piece of ferric oxide with magnetic field intensity 10 power 6 ampere per meter and susceptibility is 1.5 into 10 power minus 3. Find the magnetization of the material. So whenever a problem is given, you have to identify the notations first and then check the unit. If the unit is given in the appropriate form, it is fine. If it requires any conversion, that has to be made. So your challenges are you have to find out the notations and also convert the units into the appropriate form. Then apply it in the suitable formula calculate it, find the answer. So that is the common procedure. Now for this problem, what is given is magnetic field intensity. So what is the notation we normally take? We take it as H. Okay, so given H is equal to 10 power 6 ampere per meter, then susceptibility is chi or chi-m. So 1.5 into 10 power minus 3, it has no units. Then what is asked is magnetization. Either we can use I as the notation or m as the notation. Both means the same. So we know chi-m is equal to I by h, which means I is equal to chi-m into h. So chi-m is 1.5 into 10 power minus 3 into 10 power 6. So what is the answer? You can use the calculator to check. It is 1500 ampere per meter. Whatever is the unit for H will be the unit for I, because chi has no unit. So this is the answer. So whenever you get problems, normally the problem will not be very challenging. The challenge will be only with identifying the formula correctly, identifying the notations, do proper conversion, then handle the calculator properly to get the correct answer. Okay, so write in proper steps, given terms, then formula. So even if your final answer is wrong, till where you are doing it correctly, you will get the marks. Okay, so we'll go to the next problem. Now read the problem. The magnetic field strength in copper is 10 power 6 ampere per meter. If the magnetic susceptibility is minus 8 into 10 power 5, minus 5, calculate the flux density and magnetization of the material. So what is given in the problem? Let us write first. Given magnetic field strength, which means H is given. Magnetic field intensity or magnetic field strength, both are same. 10 power 6 ampere per meter. Then susceptibility is given. Chi-m is equal to minus 0.8 into 10 power minus 5. Because it is diamagnetic, the value is negative. Okay. Sometimes that can be asked. They give this and ask you to find out what kind of magnetic material. So on looking at the sign of the susceptibility, you can find out whether it is diamagnetic or paramagnetic. Okay. So chi-m is equal to I by h. So what I want is magnetization. That's what is asked in the problem. Okay, so I is equal to chi-m into h. So chi-m is minus 0.8 into 10 power minus 5 into h is 10 power 6. So you get minus 8 ampere per meter. So I am getting the intensity easily. So next one is flux density. So flux density, you know the formula connecting the mu and h. Okay, that is B is equal to mu h. So for which mu is required and mu is not given in the problem. So you have to find out first mu. So you know the formula for mu r, relative permeability, as mu r is equal to 1 plus chi-m. Correct? So 1 minus 8 is it the answer correct? It is 0.8 into this one is 10 power 1 So 8 ampere per meter is correct. See here, what has to be put? Chi m is what? Minus 0.8 into 10 power minus 5. That is the thing. Okay. Sorry for making a mistake. So I am using calculator to find this. I am doing it now. So I am getting the value as 0.999. That is my mu r. Now I have to find out mu, correct? So mu is equal to mu naught into mu r. So mu naught is 4 pi into 10 power minus 7. Mu r just now I have calculated as 0.999. Okay, so I will get the value, some value I will get, which I don't substitute in detail. So now I will use B is equal to mu H formula. That is the thing I want. Flux density I want. Now look at the question. Flux density is B. So B is equal to mu. Mu is 4 pi into 10 power minus 7 into 0.999, and H is given in the problem as 10 power 6. So 10 power 6. So what is the answer? Do it in the calculator. It is 1.26 Weber per meter square. That is the unit for flux density. So this is how the problem has to be done. So magnetization is easy because two terms involving that is given in the problem itself. So you found this one easily. But the flux density, it is not directly, the terms are given, required terms are given. So we know B is equal to mu H, and in this mu is not given. So to find out mu, I have to first find out mu r, because mu is equal to mu naught mu r. So mu r is equal to 1 plus chi m. So chi m is given in the problem. Substitute that, you get mu r. Then substitute in the formula for mu. You get then you substitute that into the formula for B. You get the final answer to be 1.26. At this point, I want to say there will be some confusion always between H and B, because when they are giving it in the problem, most of the times they will use magnetic field as the text to represent both H and B. So you can always look at the unit. If ampere per meter is given, means it represents field intensity. If it is Weber per meter square, means it is flux density. Okay, so that has to be kept in mind. So we'll go to the next problem. So another simple problem. Just look at the problem. Calculate the magnetic moment per unit volume in copper when subjected to a field intensity of 10 power 4 ampere per meter. The magnetic susceptibility is given. So what is asked is magnetic moment per unit volume. So what is it? It is nothing but intensity of magnetization. You should remember magnetic moment per unit volume. When we define intensity itself, we say that it is representing magnetic moment per unit volume. Okay. So instead of asking us intensity of magnetization, they are indirectly asking it magnetic moment per unit volume. If you know the definition, that is theory, then you can do it perfectly. So then once you find that, it is a simple one because it is given directly. H is 10 power 4 ampere per meter. Then chi m is given as minus 0.5 into 10 power minus 5. So what is asked is intensity of magnetization, which is chi m into h. But intensity of magnetization is not directly questioned in the question. You have to note that. That is why I have chosen this problem to solve. Okay, instead of giving this, they have given the meaning for this, that is magnetic moment per unit volume. So this is equal to this has to be found. So that is a small challenge given to you in this problem. So minus 0.5 into 10 power minus 5 into 10 power 4. So the value is 0.05. That is ampere per meter. So this is the answer. So once you find it is I, then the problem is simple. Okay. So with this we complete this problem. So with this we have completed this video. So do as many problems as possible. Practice more problems. The problems will not be very challenging. Only with practice you can write the examination well. Okay. Thank you, students.